Hi, my name is Brian Caffo, and this is the lecture on independence in the Statistical Inference Coursera class in the Data Science series. This class is co-taught by my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So let's talk about independence. And so if we're talking about events, independence has a very intuitive meaning. The probability of the intersection of two events, A and B, being the product of two probabilities, implies that the two events are independent. And we do this very naturally. I think we multiply probabilities very naturally, and we're intuitively thinking of them as independent. So, and then we can say two random variables are independent if the probability that they're in some sets, A and B, factors into the probabilities themselves. Okay, if A is independent of B, then these statements are true. A complement is independent of B complement, and so on. So, like I said, I think we do this rather intuitively. At this point, somehow it's been sort of trained into us. What's the probability of getting two consecutive heads? If A is the event that we get a head on flip 1, B is the event that we get a head on flip 2. Both probabilities are 0.5. We want to know the probability of getting a head on flips 1 and 2. Then we would simply multiply the probabilities and get 0.25. Okay, so the ability to do that is a consequence of independence. Let's talk also about this example where multiplying probabilities can cause problems. In volume 309 of the journal Science, they report on a physician who was on trial for expert testimony in a criminal trial, and he was estimating the prevalence of sudden infant death syndrome. The person's name was Dr. Meadow, and he estimated that the prevalence was 1 out of 8,543, and then he suggested that the probability of a mother having 2 children with SIDS was simply the product of that probability. So he was assuming independence, and the mother was on trial and eventually convicted of murder. And there's a variety of interesting discussion points from a statistical perspective on this testimony in this case. For example, even if the probability is very low, if there are lots of, eventually, by chance, something will happen, and if we seek out that one chance occurrence and convict people of it, then that doesn't seem like a effective use of the legal system. But more important to this particular discussion is whether or not he should have simply multiplied these two probabilities, because that's what we're talking about today. So, for the purposes of this discussion, the assumption that the probability of having SIDS within a family are independent is what we believe to be the primary mistake. So in other words, the probability that the probability of A when intersect A2 is not necessarily equal to the probability of the product of the probabilities. And why would this be? Because if it's biological or environmental or whatever, that would be shared within families often. And then I just want to reiterate, there's many other interesting statistical points for this case. As I mentioned before, even if the probability was very low, is that compelling evidence to convict someone of murder? Anyway, there's many interesting components to this, but for the time being, let's just use this as an interesting illustration of instances where we should not have simply multiplied probabilities. So here's a useful fact that we'll use in this class, and if it seems a little confusing, I think you should just wait for the examples. If you have a bunch of independent observations and they have mass functions or density functions, then their joint density function or joint mass function is simply the products of the mass functions. And we'll show you how we use that a lot when we talk about likelihoods. So there's a specific specific sampling model where part of it is predicated on independence that we use a lot, so-called IID sampling. What are IID random variables? They are independent and then also identically distributed. So not only are the random variables independent, but they're from the same distribution. They're repeated. So coin flips, right? We think of coin flips as IID. They're draws from the same, we think the coin flips are random draws from the same distribution that puts probability a half on each outcome. So IID random variables are going to be our default model for random samples, or our default model if we are willing to assume that data is a random sample even if it hasn't been sampled that way. And then most of the standard theories of statistics are founded on an assumption that variables are IID. Okay, so let's go through an example. Suppose we flip a biased coin with success probability p n times. What's the joint density of the collection of outcomes? Well, these random variables are IID. Each of them has density p to the xi, 1 minus p to the 1 minus xi. We've seen that before. So the joint density, the probability for the combination of ones and zeros from n coin flips, is this guy, and it's going to just be the product of the individual densities. And if you do the mathematical, if you do a little bit of the mathematics, this works out to p to the summation xi, 1 minus p to the n minus summation xi. That implies that the probability of any sequence of ones and zeros, if you do 4 coin flips, the probability of this sequence is going to be the same as the probability of this sequence, or this sequence. Because in each of them there's 2 ones and 2 zeros, and see that the probability only seems to depend on the total number of successes and the total number of failures. Okay, and we'll use these kinds of independence probability calculations a lot. So I think you'll see them coming back again and again. Another interesting population parameter, which of course has a sample analog, is the covariance between two random variables, which is defined as the x minus its mean times y minus its mean expected value. And this has a shortcut formula, which is expected value of x times y minus expected value of x times expected value of y. And sort of covariance is sort of a measure of how unrelated two random variables are in a specific sense, the linear relationship. So the covariance of x and y is the covariance of y and x. Covariance can be negative or positive, and it turns out that the absolute value of the covariance is less than the product of the standard deviations. This one, right, which right here, let me just write this as standard deviation of x times standard deviation of y. Well, this one, this last property, lent someone, Galton, I suppose, to make this definition that the correlation is the covariance divided by the standard deviations. Now the covariance can be anything. The correlation is between -1 and +1. Okay, so the correlation is only 1 or -1 if the two variables are linearly related for some constants a and b. The correlation is unitless, right? So covariance has units of x times units of y. Standard deviation of x has units of x. Standard deviation of y has units of y. So divide that all out and you get a unitless quantity. Two random variables are uncorrelated if their correlation is 0, and equivalently they are uncorrelated if their covariance is 0. And the more positively correlated they are, the closer this is to 1, and the more negatively correlated they are, the closer that is to -1. So that's how we interpret correlations. And again, this is the population correlation, which is a statement about the joint density, the joint population density of the x and the y's. There's the sample correlation, which is an estimate of the population correlation. Let's go through some very quick and useful results. If we have a collection of random variables, when the random variables are uncorrelated, the variance of things like this, summation ai xi plus b, where a's and b's are some constants, is we pull the a's out and they're squared. The b's don't do anything because shifting things doesn't impact the variance. And we wind up with the sum of a squared times the variances. And the most kind of important case of that is the variance of the sum is the sum of the variances when the x's are independent. If they're not independent, that's not true anymore. So the statement is, therefore, it's sums of variances that tend to be useful, not sums of standard deviations. So in other words, the standard deviation of the sum of a bunch of independent random variables is the square root of the sum of the variances, not the sum of the standard deviations. So anyway, it's the variance is the scale on which you sum, the standard deviation is not. So here's an important subcase of this idea. That remember, the sample mean of a bunch of IID random variables, right, is just 1 over n times their sum. So if we want variance of that, we can move the 1 over n out, and it gets 1 over n squared. Then we have the variance of the sum. The variance of the sum is the sum of the variances if the x's are independent, and we assume they're IID. All of them, they're IID, so they all have the same variance, sigma squared, and so we're adding up sigma squared n times, so we get n sigma squared. So n sigma squared divided by n squared works out to be sigma squared over n. So what does this mean? It means that if, take dice as an example. So if we have x1 up to x10 are 10 dice, we have them in our hand, and we roll them, and we take the average, and we get x bar. That random variable, x bar, is random, and it has a probability mass function. At the least, it can be 1 if you get all 1s, and the most it can be 10 if you get all 10s, those results being quite unlikely. And then they has some distribution in between. Looks mostly like a bell curve, in fact, in between, but it takes it at specific values. We could figure out what that distribution is. Well, first of all, we know what it's centered at. It has to be centered at 3.5. But now what we're saying is we know a second thing, which is we know the variance of that distribution without actually figuring out what that distribution is, right? We know that its variance has to be the variance of a die divided by n, okay? It's a highly important result. And so this guy, the sigma divided by square root n, the standard deviation of the mean, is called the standard error. It's so important, it's given its own kind of name, the standard error of the mean. Okay, so let's recap some of these statements. When the x's are independent with a common variance, the variance of the sample mean is sigma squared over n. And sigma over square root n, the square root of that, is the standard error of the sample mean. The standard deviation of the sample mean, also called the standard error of the sample mean. And so this, let me just put that in a long sentence. The standard error of the sample mean is the standard deviation of the distribution of the sample mean. So we just created a new word, I don't know, just to be confusing. But I think more so we created that new word because the standard error kind of refers to a statistic. It's the standard error of a statistic. It's the standard deviation of a statistic, whereas the standard deviation is this general term. Whenever we talk about standard error, we're talking about something that's used to talk about uncertainty in a statistic that we're interested in. So it's in this case, we might talk about the difference between the standard deviation of die rolls, which is sigma, versus the standard deviation of averages of 10 die rolls, which is sigma over square root 10. So this talks about how variable sample means of 10 die rolls are, and this talks about how variable die rolls are. So to make sure we know which of the two we're talking about, we often give the one that's the statistic, we call that the standard error, even though both are technically standard deviations. The easy way to remember this, I know it sounds confusing, but the easy way to remember this is the sample mean has to be less variable than a single observation. Therefore, its standard deviation is divided by square root n. Notice when I say less variable, I'm not talking about calculating, in this discussion, we're not talking about sample anything, right? You might think to yourself, oh, I can't calculate the variance of a single observation, which is true. What you mean is you can't estimate the variance of a single observation. But again, what we're talking about here are the population quantities, the variance of a draw from a distribution. That would be sigma. The variance of an average of 10 draws from a distribution, that would be sigma over square root 10. Now in both these cases we need to estimate them, and in both these cases we need multiple observations to estimate them, in which case we'll plug in the empirical variance to estimate these quantities. So in fact, let's just define the sample variance. The sample variance is remember the true variance was the population average deviation from the true mean. The sample variance is the sample average deviation from the empirical mean. Okay? Right? Sample average deviation from the empirical mean. Well, squared deviation, I should say. Okay? And notice we divide by n minus 1 instead of n, which is annoying, but it's true. And we do that for a reason we'll discuss. But this guy, s squared, is an estimator of sigma squared. The numerator has a quicker calculation that you can do, which is exactly analogous to our expected value of x minus expected value of x squared minus expected value of x quantity squared. Is exactly analogous to that approximating the variance for the population calculation. And so anyway, the sample variance is very nearly the mean of the squared deviations from the mean. If we divided it by n, it would be exactly the average squared deviation from the mean, but we don't divide it by n, we divide it by n minus 1. So here's the reason why we divide by n minus 1. It's actually, given the tools that we've learned in this class, pretty easy to prove. The expected value of the numerator of the sample variance is, we can move the sum out of the expected value, and well, we can convert this guy to the quick calculation formula, and that gives us that guy minus that guy. Okay. Expected value of x squared, let me just say, if remember that the shortcut formula for the variance of a random variable, let's say w, is expected value of w squared minus expected value of w quantity squared, right? So that variance of w plus expected value of w quantity squared is equal to the expected value of w squared, okay? So here, if we want to calculate the expected value of the mean squared, we can plug in expected value of the mean squared plus the variance of the mean. The n's out there. And then we can do the same thing here. That would be the variance of xi plus mu squared, which is the expected value of xi quantity squared. Okay? Then the variance of xi is sigma squared, and the variance of x bar is sigma squared over n. Just simply churn through the calculations, and you get m minus 1 sigma squared. So now if you divide both these sides by an m minus 1, right, then you get that the expected value of s squared calculated with the n minus 1 in the denominator is sigma squared. So that's the reason why we do it. S squared calculated with n minus 1 is unbiased. S squared calculated with n is slightly biased. If you didn't follow this, don't worry about it. This is nothing that we'll quiz you about, and I know that for several people in the class, probably it's been a while since they've taken a math class, and this is maybe a bit much of notation. So I wouldn't worry about this too much. Here's the way to think about this. If I were to roll my dice, my 10 dice, and take the sample variance and do that over and over again, I would know the distribution of variances of 10 die rolls. I'm sorry, I would know the distribution of sample variances of 10 die rolls. And I would like that distribution to be centered at the actual variance of die rolls. And that's what dividing by n minus 1 forces it to happen. So hoping to avoid some confusion. If we have a bunch of IID random variables with mean mu and variance sigma squared, then the sample variance estimates sigma squared. The calculation of s squared involves dividing by an n minus 1. Then if we divide s by an additional square root n, or s squared divided by n, then that estimates sigma over square root n, the standard error of the mean, or s squared over n estimates the variance of the mean. And S over square root n is called the standard error of the mean, the sample standard error of the mean. Okay? So don't confuse the dividing by this square root n, which is calibrating the fact that means are less variable than the observations that they were drawn from, with dividing by the n minus 1, which is what we do just in the process of calculating s squared itself. Okay, so let's look at this father-son data, and I'm just going to look at the son's height. This is in the using our data set here. And then I'm just going to define x, so I don't have to keep grabbing the variable from the data frame. And n is the length of x, and there's no missing data in this case, or any outliers or anything like that. So let's look. So here I'm just calculating the variance manually, showing that it's the sum of the squared deviations around the mean, but divided by n minus 1. And then here I just do var x, and then see that they're both the same number. Okay, so if you didn't trust me, then there's your semi-proof that R at least does the same thing. And then, so let's compare this guy with this guy. Okay, so that's 7.92 with 0.01. Okay, so this variance talks about how variable sons' heights are, right? It's trying to talk about how variable, if these sons are a random draw from the population of sons of some interest, of male children of interest, then this is talking about how variable their heights are. This is talking about how variable averages of heights of male children are. Okay? So that's the difference. This talks about, so we don't, notice we don't have directly the information to estimate that variability, right? Because what would we need to estimate the variability of averages of children? We would need lots of averages of children. But the theory says that under the sampling assumptions, under the model assumptions, we don't need lots of averages. We know what it is from the quantities which we can estimate, which is the variables of children, not variables of averages of children. Okay, so averages of heights of children. So that's what this calculation is beneficial for, right? We only get one average, whereas we get lots of individual observations. Those lots of individual observations give us the ability to estimate the variability in male child's heights. The one average does not give us the ability to estimate the variability in averages of children's heights. However, the theory again says that we know we can relate that variability back to the variability in the population itself. And then the square root of these two quantities is the standard deviation. And so this is now, and standard deviations are just more interpretable because they're in the units. So so the height's measured in inches, this is in 2.8 inches, and this is in 0.09 inches, whereas these are in inches squared. Okay, so hopefully that frees up some confusion about the difference between the standard error of a population and the standard error of the mean and the variance of the population itself.